Welcome to ClickMyProject.com. Now we discuss about the product for low cost high performance VLSI architecture for Montgomery Modular multiplication. Next we see the abstract for the product. In many public key crypto systems, modular multiplication with large integer in the most critical and time consuming operation. Therefore, the numerous algorithm and hardware implementation have been presented to carry out the modular multiplication more quickly, and Montgomery algorithm is one of the most well known Montgomery algorithm. This algorithm too determines the quotient only depending on the least significant digit of operands to replace the complicated divisions in conventional Montgomery multiplication methodology. These kind of systems to apply the input and output operands for the ABNS of the Montgomery multiplications are represented in binary, but intermediate results shifting and modular operation additions are kept to the carry save format and to avoid the unwanted carry propagations additions for overall modular multiplication architecture. However, the format conversions from the carry save format and to final modular product into binary representations is needed at the end of each modular multiplication operation. This conversion can be accomplished by an extra carry propagation order reusing the carry save order architecture containing the SCS strategy for FCS strategy, maintaining the input and output operations for overall Montgomery multiplication methodology. Nevertheless, this strategy implies that the number of operands will increase and that more CSA and registers for dealing with these modular multiplication possibility have higher hardware complexity and longer critical path SCS multiplier. This paper presents a simple and efficient Montgomery multiplication algorithm such as the low cost and high performance modular multiplier can be implemented according to the proposed multiplier receives and output the data with binary representation and uses the one level carry save adder to avoid the carry propagation at each addition operation. These carry save additions are used to perform the operand pre-computation and formal conversion from the carry operational save format to the binary representation and leading to the low hardware cost and shortest critical path for overall modular multiplication methodology. This is the final process for our overall architecture. Next we see the flow diagram for the product. The input data bits to apply to the input data register for overall shift and add functions for modular multiplication methodology, and the clock and reset control to control the enabling signal for overall architecture based on the ring counter functionality. The ring counter functionality to enable the each and every selection line and to get it to the each B input register for bit by bit in every times. The shifting must to be selected by the every times and to apply the ring counter selection logic and to set the bypass section and feeder point section. The bypass section to control the add section and directly passing for each and every B output results. And every time the B output to be set, B bits to be set in 1, the A input to be passing to the add section, or the B input to be set in the 0, the A whatever the feeder section output to be directly passing to the add sections. Each and every times this function to apply to the shifted based function for overall modular operations. This output to be mainly based on the A cross B for overall modulus functionality. This multiplier to reduce the unwanted carry save addition process for overall architecture. These are the final output for the multiplier output, and then to passing the Montgomery functionality. The Montgomery functionality to reduce the division operation for overall modulus function. This function to apply the A cross B output to be passing in the any one of the register elements and to add the n modulus function. The n data to be added to the A cross B multiplier register functions and the output to be subtract from the each and every modulus function. The subtract to every time we can compare to the n modulus functions and less than to the given output value. If the condition to be satisfied, the final modulus output to be getted to the final architecture. This is the flow diagram for overall modular function for Montgomery methodology. Finally, we see the output for the product. This is our the Xilinx IC project for our required modular multiplications methodology. These are the programming files. Then we go to the simulation based process and select and simulate behavior model for required modular multiplication methodology. This modular method to implement the two kind of functions. One is the shift add based multiplication method and another one is Montgomery method. First we apply the reset signal and to passing the one and to apply the clocking for each and every B register controlled output. Then to passing the selection for each and every time, so apply the 16-bit output for our modular output. When this position is n to the and the final output for the required multiplied output, and these are the modulus functions, and 2 is the modulus output for overall architecture. These output architecture do mainly based on the Montgomery methodology for overall modulus operations. Then we go to the implementation based process and to analyze the RTL and technological diagram for required overall output process. These are the RTL diagram, and we go to the synthesis report for our required device utilization summary and the timing summary for required architecture. These are the device utilization summary for slices, lookup tables, and the flip-flop pair and the bonded input for architecture for overall running process. And we go to analyze the device utilization summary for timing summary. These are the running time and the frequency and the delay, latency time and the path delay time for overall Montgomery methodology for 8-bit, 16-bit architecture. These are the final output for overall Montgomery modular multiplier architecture.